Okay, hello everybody. Welcome back to the modern dynamical systems. In the meanwhile, while we are studying some results in dynamics, a huge event in dynamical systems as a part of mathematics happened. Maybe you heard that there exists a very prestigious prize in dynamical systems. It's named after Brin, because Sergey Brin, the co-founder of Google, is the son of famous dynamist Misha Brin. Misha Brin works in Maryland, and in honor of his father, Sergey established a prize for outstanding results in dynamical systems. And Mikhail Brin is a head of the jury that every year awards some outstanding mathematicians. Among the people that we mentioned briefly, for instance, Artur Avila won this prize. And there are many outstanding mathematicians. Giovanni Forni also had it some years ago, Amrisa Rig, Karina Ulchigrai, and so on. And last week it was awarded in 2024, so it was given to Muhammadi. And Muhammadi is the co-author of these famous results that I mentioned last time, the one proved by Eskin, Mirzakhani, and Muhammadi. So I recall you what was the context. We discuss now Ratner's theorems, and we deal with unipotent flows and in homogeneous space. And Eskin Mirzakhani and Eskin Mirzakhani Muhammadi established some kind of analog of these results for the geodesic flow in certain modular spaces for the action of SL2R in the modular spaces. And they made the similar type of statements with a full classification of the possible geometric shape of the orbits. They showed that it's necessarily an orbifold, and they also classified the invariant measures. I hope that at the very end of our course in May, we will have an opportunity to take a very brief look at this part of mathematics. But in any case, already by the results that we have covered up to now, you may have a very first idea what was Muhammadi awarded for. And it was a kind of the contribution into the analog of Ratner's theorems in different contexts, more geometrical context if you want. So at the very last lecture, we started to discuss the following important stuff. We formulated all the Ratner's theorems and discuss what do they mean, and then we decided to concentrate on a kind of a baby example, but it's baby only in a very, still in a very strict way to judge, because it still takes a lot of time and at least 20 pages of a very dense mathematical text. So it's the following theorem. And the theorem states that we are given a Lie group and a discrete subgroup. And we have a subgroup isomorphic to SL2R. And then we claim that any H invariant and the ergodic probability measure
sorry, ergodic in the sense that every H invariant set has a
yes.
or one measure.
Probability measure mu on the quotient space is homogeneous in the following sense. That there exists a subgroup, a nice one, meaning that it is closed, connected subgroup we denoted it by L in G. This subgroup contains our H, which is SL2R, so such that mu is more than just H invariant, it's L invariant. And moreover, there exists also some x0 in X such that the L orbit x0L is closed and supports L. Supports mu, sorry. So in other words, this mu is in reality a volume, L invariant volume measure on this set, x0 L. x0L, so sorry, bad English. x0L. So that's the theorem we stated last time. And last time I told you that I will follow the presentation made by another outstanding mathematician, Manfred Alzidler, the one who works at in Zurich. And he kind of combined some general ideas by Ratner, approaches by Margulis with particular knowledge of the properties of SL2R, and produced a relatively elementary proof. It's not elementary from any human point of view, but with respect to the general proofs of Ratner's theorems, it's much easier. If you got excited about the subject and you absolutely want to know how to prove Ratner's theorems in the full generality, I can recommend you to read a book by Dave Morris. This book is dedicated to the Ratner's theory, and he starts from some very introductory topics, as we also covered. For instance, discuss the lattices and their properties, and makes a complete presentation of the whole theory. But I think for us it's too ambitious plan, so I suggested you just to concentrate on a more specific statement. And already with this statement we got very, very tired in the previous lecture, because we started to study it and we saw that it's not so elementary. So I will try to outline the structure of the proof. Some things we already discussed previously. I will just refer you to this. In some things I will skip the proof, but I hope that the general plot will be still explicit and visible. So the complete reducibility. Is the following statement. So we took SL2R and we assume that it acts linearly and smoothly on some vector space. Since we are in the R world, I will assume that we work on a finitely dimensional real vector space. Vector space. I will denote it by V. Assume that W is an SL2R invariant subspace of V. Then we claim that we can find a complementary set that will be also SL2R invariant, so that our V will be just a direct sum of this W and its complement. So we claim that it will be very reducible, completely reducible in this sense. So we claim that there exists W prime such that it's complementary to W, and W prime is also SL2R invariant. So we say that this W is isomorphic to their direct sum. I think we were able to cover it last time. It was among the ingredients that we discussed that were needed for this proof. So I will just mention the following corollary from this fact. The corollary is that if you take any finitely dimensional representation of SL2R, and then you can make it to be a direct sum of irreducible representations.
Sorry, smoothly, is it needed in this lemma?
You mean, is it needed in the proof?
I think we can construct some sort of SL2R invariant scalar product to prove this fact by constructing some integrals on compact group, but is it needed as smooth?
I think you need, in reality, you will need some kind of, once again, Lie group structure, because you will use some adjoint representative operator for it, so it's better to keep it. So it's, you can see it as a direct sum of irreducible representations. Now, assume that, let's go back to the action of the unipotent flow. You remember, in this business of Ratner, we always deal with the unipotent matrices. And so we will consider the unipotent subgroup. It's not related to what I said before. This is just a generic property that you can prove with linear algebra instruments. And this is more about the dynamics. So this is a unipotent subgroup. And my next lemma, lemma 2, is that we take the SL2R action on some real or complex vector space. We always deal with finitely dimensional case. And then we claim that this action, this word unipotent means something, so that this action is indeed unipotent. So the action of any element of U on V is unipotent. Once again, we discussed it briefly last time. So now I will mention the third lemma that we also discussed, but this is a key statement that even has its own surname. It's called Mautner phenomenon. Maybe you remember what happened on the previous lecture. I recall you that we stated this Mautner phenomenon, and then we discussed that the classical Hovey-Moore theorem is a corollary of the Mautner phenomenon in the context of SL2R group. So I suggested you this Hovey-Moore theorem as a possible topic for the presentation, but since nobody took it, we had to reprove it in our last lecture as the next lemma. So what is more important, to keep the statement of the theorem or to keep the statements of lemmas? How do you think? What I should erase first? Probably I can erase lemma 1, okay? Because it's easy to recall, the statement is very natural. You just say that you make. Окей. Но лем так много, что нас это не спасет.
We say that what we mean by U on V is unipointed, then the linear operator of U is unipotent operator in sense of matrices.
Yes, yes, yes. So now let me recall you lemma 3. And this is called Mautner phenomenon. So we take some rho from SL to R to U of B, be a continuous unitary action on a Hilbert space V. And this V can be infinitely dimensional. It's not the V that we had there, so we don't claim that it's necessarily finitely dimensional. And then any vector of any vector, say V, I have to keep from here, which is fixed by U, so U is a subset of SL2R. So you take some vector, it's fixed by U, but in general it's not it should not be necessarily fixed by the action of the whole SL2R, yes? In general, you just say that it's fixed by the action of a smaller subgroup. But what Mautner phenomenon says that it is also fixed by the action of the whole SL2R. We discussed it once again on the last lecture, and we also discussed its connection with the Moore ergodicity theorem. I recall you briefly what is Moore ergodicity theorem, very useful tool. So you had some group G, you had an irreducible lattice in it, and you said that if you have some closed non-compact subgroup in your original group, then this subgroup acts ergodically on the quotient space. So on the first glance it's not related, you just discuss what happened to this action. But if you work a little bit, you can see that the Moore theorem in case of SL2R containing groups can be reduced to this statement. So despite of the first impression that it is something in the world of Hilbert spaces, and it may be some statement from functional analysis but not from dynamics, in reality it admits a presentation in the language of ergodic theory as well. So that's what more or less we observed at the previous lecture, and then we stated the following very important proposition, and we started to prove it, and we did a very, very little progress in it, and then I understood that everybody is tired, there were not many people, and so I gave a freedom to my small auditory. So it makes sense to repeat it probably. So the proposition was as follows. I know that we can see it on the camera, but is it comfortable for you to look at this blackboard as well? Not very comfortable, okay, then we can erase something. Ну пусть она, наверное, живет, потому что все-таки... Ну да, но просто это цель в жизни. Вот, поэтому пока... То есть The plan is as follows, that I will try to show you the list of statements we need to prove on our road to the general statement, and then on some statements I will comment more, provide more details, and some we will just leave as an exercise and so on. So the proposition is as follows. I call it proposition 1. Morally, the sense of this proposition is very easy. I want to say that the lack of concentration implies additional symmetry. Now I will explain what these words mean. Implies. So we take our G, H, gamma, mu as in the main theorem. That was the motivation not to erase the main theorem. Otherwise I would need to repeat all these notations, but now you can see it immediately, so let me just say that they all are like in theorem 1. So suppose there exists a closed, connected subgroup L. And L is between G and H. So it contains H in particular. And we say that mu is L invariant. So this is, in the statement of the main theorem, we said that there exists L with this property, and now we assume that such an L exists, but then exactly one of the following statements holds. There are two opportunities. The first option is concentration takes place. Concentration means that mu is supported on Lx of L. So Lx0. So it's supported on one orbit for some x0. So it's exactly what we stated here. Понятно, да? У нас вот здесь было предположение, что мы говорили, что если вот эти все условия выполнены, то есть такая подгруппа L, которая между ними такая, что мера будет L инвариантна и при этом концентрироваться на этой штуке. Значит, в нашем утверждении мы пока утверждаем меньше. Мы говорим, если нам откуда-то выдали такую L, пока не знаем, откуда она взялась, почему нам так повезло, но откуда-то нам выдали такую L, что она оказалась, оказалась L инвариантна, и L при этом между H и G, тогда одна из двух опций имеет место. Первая опция – это то, что происходит то, что тут написано, что мера садится на одну из орбит. Либо, если этого не случается, значит, есть вторая возможность. И вторая возможность такая. Another option is the additional symmetry. This means that there exists yet another subgroup, closed, connected, as we like. L prime, that is greater than L, still a subgroup of G, such that mu is L prime invariant. Now you probably understand why I said that the sense of this proposition is that lack of concentration implies additional symmetry. So either our measure is concentrated on the orbits of this subgroup, Either there is a huger subgroup such that mu is still L prime invariant. So now what's the general plan of the proof of the theorem we are looking for? Okay, we are still missing the construction of this L, but at least how to get from this proposition to the theorem, it's quite clear.
Is it there? Is it there because L is a connected part of group of all invariant?
Exactly. Exactly. So if your L was not good enough in the concentration sense, you just replace it by L prime due to this theorem, right? So either you were given this L and it was immediately very good, either L prime was not very good, I'm sorry. Either this L prime is not very good, but L is not very good, but then there exists L prime, which is greater than L, and so I can replace my L by L prime, and so I can ask myself what's going on here and repeat. Now I examine my L prime. If L prime gave me the concentration statement, I'm happy. If it did not give me the result I want, then I can always find the L double prime and repeat. So at some point, I'm supposed to arrive to the statement that if I was given such a subgroup with this property, then I can achieve this concentration statement. So our purpose of the life now changes. This was the previous purpose. Now we need to prove this proposition 1. And then if we prove the proposition 1, we will need to understand how to construct this L, the first L, and then we will apply the iteration process that we discuss now.
I'm sorry, but remember in last lecture we constructed L as a connected subgroup of all elements such that mu is G invariant. But if we have an L prime, it must contain it in L due to definition of it. So this is connected subgroup, so it must be just an L.
Yes, exactly. Yes, so what I said here that you put an iterative process was if you don't know how L appeared, if you just have no idea, you were just given it somehow, then you run it as an iterative process. But then if you choose at the first glance L smartly, then your argument works, and this proposition implies what I say. You understand? So that's just a kind of different way to start, but in any case, this proposition leads us to the statement we are interested in. If we find L smartly at the beginning, then we use it and we are given the result. So we want to know how to prove this proposition. And this we also will split into several steps. First, we state the following lemma. This lemma is quite hard one. So on our first attempt, I skip its proof. I try to build the whole building of the general logic of the proof. And then if we will be strong enough, we will go back and fill the gaps. If we feel tired, I just address you to the original paper by Ann Zidler. It's up to us. So lemma is as follows. Suppose that, of course, all the elements are like in the statement of proposition 1. Suppose that there exists x0 such that the measure of the orbit Lx0 is strictly positive. Then Lx0 should be closed and mu is supported on Lx0. If we have such a lemma, then we can, and we want to prove the proposition 1, then of course at the moment when we find some point with this property, we are done. Because we realize this option, that mu is supported on this orbit. So if we believe that what we said in lemma 4 is true, then in order to prove proposition 1, we have to assume, and we want to prove from contradiction, we have to assume that this never happens, right? Because once it happens, we are happy and we know what to do thanks to lemma 4. So now we assume that mu is totally non-concentrated on all orbits. So let's do it. What does it mean? It means that mu of the orbit is just 0 for any x from our homogeneous space. It's an important equality, and I will mark it. So if we take some random x and y, then we can assume, you see, any orbit is very small from the measure point of view. So with probability 1, if you fix x, then any y will not belong to the orbit of x. They should not live at the same orbit, right? If that is true. So y?
Almost all.
Mm-hmm. For mu, almost all x and y. Но это как раз то, что у нас носителем этой меры является наше множество. Соответственно, если мы верим в лемму 4, мы ее не доказали, это много работы, но предположим, пока что мы уверовали в нее. Просто если мы сейчас будем... Мы хотим доказать вот то утверждение, потому что мы понимаем, что благодаря ему мы, в общем, представляем, как доказать итоговую теорему. Поэтому мы будем доказывать это утверждение. И мы предположили, что мы поверили в лемму 4. Мы ее докажем позже, если будем достаточно сильны духом. Если не будем, ну, я просто там набросаю какой-то план. Значит, пока мы сказали, лемма 4 верна. Тогда, получается, если вы нашли какую-то орбиту, у которой положительная мера, то у вас уже доказано утверждение 1, потому что реализовалось вот это предположение. Уже не надо строить никакой L'. Уже все хорошо на этом этапе. Значит, у вас должно быть такое, что все орбиты имеют нулевую меру. И из этого мы утверждаем, что для почти всех по отношению к этой мере x и y у нас y не лежит в орбите x. И наоборот. So, informally, what does it mean? It means that the group elements in G that are used to move from X to Y, they should be somehow transverse to L, right? So it's not a real statement, it's just informal explanation, that you have some kind of transversality within the path inside of the group G that would take us from one point to another, and the path of the subgroup L. But at the same time, mu was not just whatever measure. Mu was a very nice measure, like in theorem 1.1 that I erased. But you remember we discussed what does it mean to be ergodic for the measure. So we remember that we required from for mu to be ergodic measure. So if we know that it's ergodic...
Mu is H ergodic.
Exactly. Is ergodic. with respect to H, yes. So if we know that, then you remember I stated some observations at the very beginning. We said that due to the corollary, this action was, it would imply that it's also ergodic with respect to U. So ergodicity we know very well thanks to Petya, who taught us how Birkhoff ergodic theory works. So we can write that.
So it's ergodic with respect to U by by
one of the, yes. Yes. So we know that almost every point, for mu almost every point, for any generic point here, if we take, so it's, we have the following genericity with respect to U. So we say that the integral of f the mu, I tell you who is f in a second, we integrate on the whole space that we have, so the whole homogeneous space, it's the limit when t goes to plus infinity, 1 over t, integral 0 t, f utx dt. So who is f? F is just any continuous compactly supported function. That takes our homogeneous space to R. So now we have to combine it with, so the corollary of this observation is the fact that we can make description of measure mu of the, in terms of U orbit of a generic point. So we will provide it in a second. But at the same time, we see that that two generic points, they are likely to be separated from each other by some group element which is transverse to L. So what do I mean? I state the second proposition. It will correspond to a very particular part of the group G. It's called the central case. And we claim that we can prove it for the central case. So this is a proposition 2. Central means that I will consider only the elements that commute with other elements. So let me explain what I mean. Нет, мы его не доказали еще совершенно. Мы пока просто, мы работаем, значит, второе предложение будет внутри первого. Мы доказываем первое. Вот. И пока мы пытаемся понять, как бы нам хорошо охарактеризовать, что же это за мера такая, используя вот все, что нам известно. Значит, я хочу сказать следующее, что if we take two generic points, generic in this sense, we take two generic points, of our homogeneous space, and we know that y is gx, and
Sorry, what do you mean by generic point?
I mean that those for whom it holds. So
Holds and Birkhoff ergodic.
So it's we say that it's true for mu almost all points, but I want to be my x to be generic in this sense, that this limit we have. So assume that I was able to find two generic points with the following properties. That, you know, they are generic points in the homogeneous space. So they are elements of the factor of G on gamma. So the elements, if they are elements of G, then we can find another element of G that connects them to each other. And in my central case, I assume that this G is an element that centralizes U. It's very rare. I only look for a very specific case now. So it commutes with element of U. So then I claim that my measure mu is invariant under the action of G. Значит, что мы здесь пока утвердили? Мы сказали, что для двух точек, которые находятся в общем положении для того, чтобы мы могли пользоваться всей эргодической теорией, если у нас получилось так, что эти точки друг из друга получаются применением элемента нашей группы такого, что он коммутирует со всеми элементами в U, это очень частный случай, да? Я не утверждаю, что таких элементов очень много. Я пока просто рассматриваю только такой случай. То тогда я утверждаю, что моя мера будет инвариантна относительно действия вот этого элемента, который мы использовали, чтобы одну точку из другой получить. Давайте опять же, я пока не буду это доказывать, а мы пока в это поверим и попытаемся углядеть следующую логику, что же будет дальше происходить. So, I claim that of course, we don't want the invariance with respect to one group element. We want to prove this statement. So we need the invariance with respect to the elements of a UG subgroup L prime, and not with respect to one element. But what we want is to generalize this statement in a way that we will leverage this former to the later, provided that one has enough group elements. So if I can find many group elements with this property, then I will be able to construct this L prime that we are looking for.
I think it's interesting because if we have y and x such that, then we can claim the same about y, G inverse at y and x. So we know that if it's called for G, we can prove
it's true for G minus 1. So what will be the next step? Давайте мы продолжим. Я сотру пока эту недоказанную лемму. Вот. Давайте мы лемму сохраним, вдруг мы ее еще будем доказывать. Но я под ней напишу следующую. Понятно, да, что в чем наша цель? Мы пытаемся доказать вот это утверждение, и пока мы научились доказывать инвариантность не относительно целой подгруппы, а только показывать, что для некоторых элементов мы такое можем сделать. Но теперь утверждается, что если мы где-нибудь натащим достаточное количество таких элементов, то нам этого хватит для того, чтобы сотворить то, что нам нужно вот в этом утверждении 1. Значит, как мы к этому идем? We go through the next lemma. That will be called lemma 5. So we preserve all the notations like in proposition 1. And suppose we are given a sequence of elements and we want that this sequence tends to identity. And we assume that each element is nice in this sense. So the action of each element preserves mu. And assume that all these elements are out of the subgroup L. Because we need to switch from L to L prime, so we are not interested in those who already live in L. So we assume that then that will be already enough to construct L prime as we want. So we claim that there exists a closed, connected subgroup of L. So it's L prime such that mu is L prime invariant. So if we would be able to find, here is the way how to find one element. And if we would be able to find the sequence of elements with these two properties, that mu is Gn invariant and at the same time this sequence goes to identity, then we know how to construct the element. So it's a subgroup of G, sorry. Значит, смотрите, мы... Значит, если у нас есть... Значит, none of the Gn belongs to L. So this, это хвост от mu. So, если все Gn сами L не принадлежат, и при этом они сохраняют mu, а из них получилось составить последовательность, которая стремится к единице, то тогда мы точно уверены, что есть такая подгруппа L', которая позволит нам удовлетворить требования из предложения 1. So, from proposition 2 and this lemma, we see that we are done if we can find pairs. So if we can find this Gn with this property from the central part, right? So what does it mean? It means that if we can find pairs that x, yn is Gn, xn, or they are nearby generic points, and Gn goes to identity, and Gn is not in L, and Gn centralizes U, then we are very happy because we know that this Gn will be good enough in a sense that mu will be invariant with respect to Gn, thanks to this proposition, and then we just apply lemma 5. So we are only missing this situation when we don't have this centralization property, so we need to think how to treat this non-central case. Ну, смотрите. Да, значит, смотрите, мы что хотим сказать, что у нас есть вот это предположение. Оно говорит нам, что если мы y смогли представить как gx, то тогда μ будет инвариантно относительно g. Но при условии, что этот g был такой, что он коммутировал со всеми из u. Если нам удалось набрать целую последовательность таких g, то по лемме 5 у нас тогда получилось и целую подгруппу создать, которую мы тут строили. А мы уже знаем, что если мы тут все построили, то и теорема у нас докажется. Но проблема состоит в том, что здесь мы накладывали очень сильные условия, а именно мы предполагали, что эти g коммутируют со всеми элементами из u. Поэтому, если вдруг у нас получилось таких набрать целую толпу, то мы молодцы. Но если у нас такого не получилось, то не хотят они коммутировать, то нам нужно находить какие-то другие способы со всем этим взаимодействовать. И нужно как-то рассмотреть, что же происходит, в этой ситуации тоже разобраться, потому что когда коммутируют, то у нас все хорошо. Давайте мы попробуем это сделать. Так как мы сейчас будем рассматривать ситуацию, когда нет нашего коммутирования, то я сотру лемму, которая про центральный случай, потому что она нам сейчас... So now we need to prepare a little bit to get the strategy what to do in case of non-central situation. So we need to consider non-central case. And suppose that we have 2 points, x and y. They're generic in the sense that we discussed before, in the sense of ergodic theory. And we assume that y is gx, but g is close to the identity, but doesn't centralize u. So the key observation here is the following fact, that we want to use u invariance to pull x and y slowly apart from each other. I will explain what I mean. So we take 2 generic points, and we say that they were generic. So their images under the action of ut are also 2 generic points. So generic as well. Now, for any t. So now if these 2 guys were different by g, what is about the difference between these 2 guys? So we say that we can say that it can be their difference is given by gt, and gt you compute it as ut g ut minus 1 minus t, right? So if you multiply it, ut g ut, you take ut x, and so ut they kill each other, and you indeed get uty. It seems it's true, right? Понятно, да, что мы сказали? Мы сказали, вот у нас было такое равенство, мы к нему будем применять наш поток. Будем смотреть, куда мы переходим под действием матрицы ut. Будут получаться, значит, образы этих точек, они все равно будут в общем положении, в смысле эргодической теории, но при этом на какой элемент они будут различаться? Вот на такой. Эти различались на g, значит, их образы будут отличаться вот на такую штуку. Ну, это можно просто подставить и проверить. У вас сойдется.
То есть хотите сказать, что ut y, ну да.
Ну, если вы подставите, у вас все честно сократится и получится. So, now we can take a log. Log gt, it will be ut log g u minus t. And for those who know what is adjoint representation, we can say that it's nothing else but exponent.
Is it definition or
Нет, ну мы просто логарифм взяли, ну как бы. Если вы, у вас ut это матрица вида 1t 0,1, поэтому.
Нет, не означает, что он вынес эти логарифмы так, может быть, что хотите сказать, просто странно, что...
Ну она же не, матрица у вас унипатентная, то есть это другими словами означает, что это единичная плюс нильпатентная, поэтому если вы это ut. Вот. Это у нас оператор присоединенное представление. Log u, log g.
Почему логарифм сходится?
Но это простое упражнение, если вы посчитаете, как выглядит логарифм унипатентной матрицы.
Не, а G у нас разве не патентно?
G у нас не унипатентно, но вы сопрягаете унипатентно.
Не, это то, что я сопрягаю, да, то есть нет, даже как. Что у нас как логарифм матрицы определяется через ряд.
Но вы можете разложить это в сумму. У вас логарифм произведения. Вы можете...
Это бог с ним, то есть ладно, бог с ним про сопряжение, вот это штука просто. Почему логарифм? То есть логарифм это матричная функция, да, он же определен не на любой матрице. Почему логарифм от G вообще существует? Вдруг логарифм от G сам по себе, ну, не входит в радиус.
Ну, мы пока ничего не доказываем, поэтому будем считать, что g мы договорились, что он близко к единице. Поэтому войдет он в радиус сходимости. Мы, да.
В последней строчке там...
Ну, мы заменили, написали присоединенное представление. T от присоединенного представления от логарифма этого.
Что такое U?
Сейчас, там, наверное, должно быть... сейчас, ну, это УТ должно быть.
Сейчас, у вас же тут написано...
ТТ вынеслось, У это, соответственно, было... Ладно, давайте мы...
Сейчас у вас тут написан ад большой, ну, то есть если...
Это присоединенное представление от логарифма этого У подгруппы, в смысле. Должно быть.
Присоединенное представление, ну, с экспонентой коммутирует.
Угу.
С экспонентой. От большой до экспонента, от экспонента от малого.
So, in any case, what I just want to say is that from lemma 2, you remember we discussed that we knew that the action of element of U on V was unipotent. So we knew, due to this fact, that the action of the adjoint representation of the log of any U, any matrix U, is nilpotent.
You're supposed to mean exponent of add logarithm ut. That's correct. Not t add log ut.
Давайте вот так напишем. Вот так.
Yes.
Ну, тогда t можно будет...
That's correct.
Ну, можно будет вынести потом. Потому что t это просто степень у вас у матрицы этой.
Ну, степень-то.
Ну, она перейдет через логарифм. So, what I want to say is that this log gt, it will depend polynomially on t. То есть мы задействуем тот арсенал, с которого мы начинали, когда обсуждали про всякие свойства наших присоединенных представлений и прочего. So, why do we need this? Because if G does not centralize U,
Why we know that does depends polynomially?
because this adjoint representation of log U is nilpotent. So if now you write up the presentation of the exponent as a Taylor series, you will see that necessarily this log gt should be a polynomial, otherwise you will not get a nilpotent action.
We know that log ut is unipotent matrices. And we know by some theorem, I forgot name, that adjoint representation of unipotent is just unipotent or nilpotent.
Nilpotent, yes.
And exponent of nilpotent matrices is a polynomial.
So if you look here, yes, you will see that it's a polynomial thing. So G does not centralize U, then log gt is not constant. So then if we have a polynomial thing that is not constant, then it should diverge to infinity when t goes to infinity. So what does it mean for us? It means that if we take some small ball B around the origin in the Lie group, it does not matter, so it's ball in the Lie algebra, and it's doesn't matter with respect to which norm you take. You take your favorite norm. So then whenever this log G was inside of B around the origin, so you take a ball around the origin and you look at this log G, and so log G should leave at some point your ball. So,
Ball in Lie algebra.
yeah, in the algebra, because you consider the adjoint representation, so.
And
So it goes to, we agreed that this is polynomial, so it goes to infinity, right? So if it goes to infinity, it should leave any balls that you may put around it. So this should be the first moment when we reach the boundary of this ball. So the ball has a boundary, and this guy will reach necessarily this boundary, and I will call G star the G that corresponds to the moment when we touched the moment of escape, when we touched this boundary. And so now we are ready to state the next proposition, and we are close to the end of the story, despite of the fact that we skipped some important proofs. So the proposition 3. Still, don't be confused, proposition 3 is a part of the proof of proposition 1. It's not an independent proposition. So proposition 3, we have the proposition 2 for central case, and we have proposition 3 for non-central case. So xn, yn are resolved in the homogeneous space. They are still very generic. And we say that yn can be computed as gnxn for some gn in G. And since we are in a non-central case, we say that this gn do not centralize U. But we want that this gn, they go to identity, because as you asked me correctly, it's important that we are not too far to use this logarithm and also to be inside of the ball at the very beginning. So we assume that that means that gn sit inside of the ball for sufficiently large n. So
by what ball?
You take norm you prefer, you put a norm around the identity here, and gn in this sense belongs to the ball.
It is not one ball, because it's one from the algebra. You mean
It's
exponential coordinates?
Yes. So then we say that we will assume that they are not just generic, but let's say that they are uniformly generic. I explain what does it mean in a second, but it does not change morally anything. So if it's true, then I claim that mu is invariant not under the action of all this gn, but under the action of G star. G star is a who? It's a limit point of Gn star. Значит, смотрите, мы с вами сказали, что будет каждый раз у нас будет момент, когда мы будем вышагивать из этого шара. Ну, потому что мы должны идти на бесконечность, в шаре сидеть не можем. Будем брать G со звездочкой, это вот этот момент, ну как вот у нас было первое возвращение, здесь у нас момент первого покидания. После этого мы тогда этой последовательности Gn ставим в соответствие другую последовательность, составленную из элементов, отвечающих этому первому выходу из соответствующих шаров. И тогда у этой последовательности будет предельная точка, и относительно этой предельной точки наша мера будет инвариантна. То есть мы что с тем самым сделали? Мы все равно научились для доказательства этого утверждения, мы научились изготавливать где-то дополнительные точки, дополнительные элементы G, относительно которых μ будет инвариантно. Если мы верим в доказательство этого утверждения, какой будет финальный шаг, как отсюда прийти сюда. Ну вот я сейчас это скажу и вас отпущу на перерыв. И вы решите, готовы ли вы, хотите ли вы доказательств промежуточных утверждений или нам хватит. То есть мой план был не рассказывать вот эти промежуточные доказательства, просто чтобы у вас схема была в голове, а элементы не доказывать, но я думаю, что мы будем слушать доклад. Но я могу доказать, как бы, для меня это не принципиально. Okay, so let me complete the proof if we believe in this proposition. So we now need to make a bridge from this one to this one. This already gave us a way to construct a new element such that mu is invariant with respect to these elements, even in non-central case. So I forgot to say what does it mean to be uniformly generic. It just means the following, that you remember we said that we had this integral to converge in Birkhoff theorem, and in this case it would be generic. So if this convergence is uniform, then we say that it's uniformly generic. So now what's the way how to prove proposition 1?
Sorry, what do you mean by uniformly generic in which sense? That convergence is uniformly, it doesn't depend on n or what?
I want to say that it does not, we said that we have this convergence, but the rate of this convergence does not depend on f. Yes.
On n?
Mm-hmm.
On n?
Yes. On n. So now we have all the proofs. So we know that mu almost every point is generic. So we can take Егоров theorem. Все напряглись и вспомнили, что они проходили на младших курсах, вот, в частности в теории меры. И so Егоров theorem in our case would imply that we can find sets E in G to gamma of measure arbitrarily close to 1. Вы можете написать здесь, там, не знаю, μ от E больше или равно 0,9 или 8 девятых. Какое у вас любимое число, близкое к единице, это не принципиально. On which points are uniformly generic? So once you restricted yourself to still a very big set where you can have this, then you take a small neighborhood of the origin in L, of the identity point in L, identity in L, and then you apply Fubini's theorem just to estimate the following integral. So you integrate over the whole homogeneous space the Haar measure on the unimodular group, and here you have V. You have characteristic function of E of x, characteristic function of E of gx, dm g d mu of x. And so you can estimate that this will be not smaller than 0.8, for instance.
Sorry, what
So
is V?
V is a small neighborhood of the identity in L. So you consider it, this is a Haar measure, and these are two characteristic functions, and this is our mu, which is our regular thing. So why do we need it? Is that finally what we get is that we can find a set E prime of positive measure such that the elements who live in E will have a measure that is huge enough. And this measure will be positive. So we will be able to apply the statement we made at the very beginning.
Почему тут 0,8?
Ну, потому что там был 0,9, соответственно, тут будет там типа больше или равно, чем 2 меры, вот эти вот, минус 1. Ну, можно написать там, ну, тут будет 0,8.
Глупый вопрос, наши просто тут два индикатора, если мы вот проинтегрируем по мере, ну, просто индикатор первый, там мера ню разве просто не сократится, там, разве не будет просто...
Ну, тут 0,8 это на самом деле 2 меры. То есть это, смысл этого упражнения просто в том, что если мы перешли от generic, uniformly generic, то мы не очень много потеряли.
Сейчас, подождите, извини, не понимаю, просто глупый вопрос, простите. Вот если вот я воспользуюсь теоремой Фубини и просто возьму там однократный интеграл по x,
Да.
у меня же мера, сейчас, тут интеграл по множеству e.
Да. У вас тут индикаторы только на Е, поэтому у вас тут будет... Ну, вы никак не получите больше, чем 2, вот, и выкинете вы, соответственно, тоже не больше, чем 1. Вот, но to put it short, so what I want to say is that at the very end we say that we have a set of E prime. So, давайте я это здесь напишу, что ли.
Это не очевидно, это упражнение.
Ну, оно совсем легкое. Вот, и оно такое классическое, то, что в теории меры заставляют делать. And so we say that the measure of all this G such that Gx sit in E can be estimated as 0, for instance, like that. So for all x in E prime. And we can state that this E prime has positive measure. So we can apply the statement that we made that if we had something of positive measure, then we could find xn, yn in such that they were belonging to different orbits, and then their distance should go to 0, so, and so on. Ну, это, как сказать, эти числа все рандомные, просто это какие-то числа, близкие к единице.
Предположим, вот мы доказали этот результат, почему мы знаем, что точки, которые...
Ну, потому что мы же с вами начинали с того, что мы обсуждали, что если у нас есть какая-то орбита, которая положительной меры, то тогда, значит, у нас все получается. Значит, мы предполагали, что все орбиты у нас меры неположительной, и значит, после этого мы говорили, что они должны все, тогда эти x и y должны все лежать в разных...
Нет, я по-другому. Как это, то есть мы знаем что это больше 0,8, откуда у нас точное равенство на вот меру...
Не-не, мы так e' определяем, это определение множества этого. Мы знаем, что это больше 0,8, и мы говорим, что тогда тех, для которых вот эта вот мера будет, какое-то положительное число на m от v, которое меньше 0,8, они все живут в некотором множестве, это множество имеет положительную меру, и дальше мы применяем то, с чего мы начинали.
То есть мы говорим, что мы рассмотрим множество таких иксов и множество таких g, что g от x лежит в e, и имеет меру, скажем, условно 0,7 мер.
Да, ну давайте мы, наверное, сделаем перерыв. Я закончу тогда после перерыва, а вы пока подумайте, вы хотите, чтобы мы доказали промежуточное утверждение или перешли к следующей теме. В качестве следующей темы как раз предлагается понять, за что, собственно, получили медали там Артур Авел и Марио Мирзахани. Ну, то есть поговорить про перекладывание отрезков, слоение на поверхности. Вот. Давайте мы тогда сделаем паузу. Сейчас мы позовем. Пойдемте, мы продолжим. Okay, so let me just try to complete more or less the proof, because there is a very little remaining piece. So what we want is basically we want to apply the statements that we already proved. So in order to do that, let's make a few small observations. So if we have our H, which is SL to R, morally, and it acts by conjugation on the Lie algebra. G, it's the Lie algebra associated with our group, and we have a subgroup, which so there is a subspace corresponding to this subgroup, which is invariant. So if we have such a thing, then the first lemma that we stated about the full irreducibility, it's an invariant subset, invariant under this section. So by this lemma 1 that we stated, we know that there is a complementary space W of L, which is also H invariant and U invariant and so on. So this is a complement, and it's H invariant, so U invariant. And we can then apply inverse function theorem and conclude that for any element of our group G, the element which is sufficiently close to identity, we can factor, we can say that this G is exponent of WL for some element of this set, which is also close to ID. And this W is also small.
Sorry, G is exponent omega of L?
Yeah, because so what we have, this is an element of the Lie algebra, and now we want to go back from, we know how to go from the group to Lie algebra, and now we want to go from Lie algebra to the group locally.
So, sorry, but I don't understand what exponent of omega times L, or it is?
Yes.
But L is a, what is it, L? It's a subgroup?
Let me check for a second.
Ну, должно быть.
Наверное, вот так должно быть.
Я просто омега L это подгруппа, подпространство странного. Элемент группы равняется.
Well, in any case, what I want to say is that you can find the map P from G to this L, which is invariant, and this will be smooth near identity, and you can say that then you can present your Yn as Gn xn, and давайте мы не будем так подробно это обсуждать. Короче, давайте упростим. Смысл в том, что мы по предыдущей лемме, значит, мы хотим понять, как нам построить это L' из L. Идею мы уже поняли, что мы будем пополнять ее за счет каких-то дополнительных элементов, а не одного вида в случае, когда у нас центральная это, и другого вида в случае, когда она не центральная. И, соответственно, в случае, когда у нас есть эта центральность, мы используем proposition 2 plus lemma 5 leads us to the additional elements. And in case when we are not in the central case, we use proposition 3 still plus lemma 5. So maybe I skip this part because it's too technical. In any case, what I want to say is simply that by application formal application of the lemmas that we stated before, we can provide these additional elements that will live in L prime and not in L, and construct L prime in this way to prove the proposition 1. Ну, то есть мы с вами научились доказывать для дополнительных элементов, которые были не в L, что μ будет инвариантно относительно них. Вот. И то, что нам осталось не совсем проверенным, это утверждение о том, почему, когда мы пополним L такими элементами, у нас все равно получится замкнутая связанная подгруппа, но это еще одно тоже.
Еще раз, то есть мы сказали следующее, что вот у нас есть два варианта. Либо мы коммутируем с группой U, либо не коммутируем.
Да.
Коммутируем, то мы же инвариантны, все хорошо. Если не коммутируем,
То мы построили в Proposition 3 тоже вот такие вот G со звездочкой элементы, для которых все равно будет наша мера G со звездочкой инвариантна.
хорошо. А почему мы умеем строить последовательность ведущих единиц?
Это как раз вот некоторая техническая работа, которая следует из первых трех лем, которые мы сегодня вспоминали. А утверждение про то, что так построено L' у нас будет замкнуто и связано, следует из нашей леммы 5. Мы сегодня доказывали лемму 5, и вот из леммы 5 это следует. А вот то, что у нас получится построить такие последовательности, это следует из общих свойств группы алгебр Ли, вот, которые как раз опираются на наши три конструкции вот, из первых трех лем. Okay, so we have two options. Either we go deep into the details of the proof of each of the block we mentioned here, either we stop at this point and we will continue to do homogeneous dynamics on Vyacheslav's talk when we will finally learn how to apply all this Ratner's theory to Oppenheim conjecture, and we switch to another part of dynamical systems, to the Teichmüller dynamics. I will tell you some very introductory things, and at some point a couple of other people will give the talks dedicated to this subject to give you a more deep understanding of it. Ну что, как мы хотим? Восстановить здесь все детали до конца или разобраться, посмотреть, какая еще бывает динамика?
Мне кажется, дальше пойти.
Дальше?
Я предпочтел разобраться.
Какие еще есть? Давайте, кто хочет узнать подробности здесь? Окей. Кто хочет узнать подробности про перекладывание отрезков там и сопутствующую динамику? Ну хорошо, вроде народ побольше. Окей. So let me show you a very simple combinatorial object. I will not today touch its geometric sense much because I will leave it as a goal for another lecture by one of the students. The object is very simple. So you maybe remember that we started our course with the study of the rotation on the circle. So we study Teichmüller dynamics. So rotation of the circle, you hopefully remember more or less what it was. So now assume that you consider the following generalization of this object. You take an interval of a real axis. Let's agree that we will include the left points of the interval and not include the rightmost points, so it will be half intervals in reality, but I will use the word interval, never mind. So we divide it into several parts, and then we mix up these parts. So what we get is a map from this half interval into itself. And this map is piecewise continuous, and in each interval of continuity, it's just the shift. Why do I tell you that it's the same thing as the rotations? It's a more general option. So let's restrict ourselves to the case of two intervals. Да.
Do you allow to rotate the intervals?
No, it's simply a shift. We don't rotate them. We don't change the orientation. It's orientation preserved in isometry now. So if we would consider the same map on two intervals, I claim that it's exactly the rotation on the circle. Do you agree that it's the same thing? If you glue these 2 points together, it will give you exactly the same map. So this guy is called interval exchange transformation. we assume that the number of intervals of continuity is finite. There is some mathematics about infinite number of intervals, but I don't want to touch it now. I think it's less exciting than the one dedicated to the general thing. So we divide the interval into several parts, and then we mix them. So on each interval of continuity, we will have some map which looks like we add some lengths of the intervals and we subtract this length, and that's how we get, it's a linear map. Right? So a few words of history. They were born in 60s in Soviet Union. It's not very clear who was the creator of them, because the first definition of interval exchange transformations on 3 intervals was given in the paper by Vladimir Arnold, who considered it exactly as a generalization of the rotation on the circle. As we discussed, rotations of the circle are closely related to the continued fractions. So Arnold was interested in continued fractions, and by chance he discovered interval exchange transformations. But there were other people who made a similar work. One was Valeria Seledets, who at that time was a student of Yakov Grigorьевич Sinai. And he made a definition on n intervals, on arbitrary number of intervals, and he told me in a private communication but that the first person who made the picture for him was not Sinai, but it was Rokhlin in St. Petersburg. So you see, many people arrived to the same idea, more or less the same time. And at the same time, Anatoly Katok and Anatoly Stepin also got the same picture. They were a little bit later, because they were working with billiards in rational polygons, and they discovered that the first return map on the transversal. So my student Masha, who is at the first year, plans to give us a talk in one of the next lectures about the connection between the billiards and interval exchange transformations. So hopefully she will be able to do it, and now I will not go much into it. Just believe me that the properties of interval exchange transformations and their orbits are very important, because you see it appeared in very different problems of mathematics. So those who started with continuous fraction discovered them. Then Sinai was interested in it, and at the same time Thurston, who was not familiar with the work of Russian co-authors, Russian colleagues, also learned about them because he was studying measured foliation on surfaces. And these people learned about them because they were interested in billiards and polygons. But all these people agreed that they would like to know just a few things. And one thing was, how do the orbits behave? So I hope you remember who is the orbit after all this study we performed. So this is an orbit, and we are interested in its possible topology, because we know what happens in the case of rotation on the circle, right? You remember that we started with a dichotomy when we discussed that either they should be closed when we rotate on a rational angle, and if the angle is irrational, then we get everywhere dense orbits. So the natural question is if the same holds for interval exchange transformations. And the answer is almost affirmative, just we should be a little bit more accurate. So in order to describe our interval exchange transformation, we need to know two things. We need to know the length of the intervals. So it will be the vector of positive numbers. And we need to know the order in which they appear in the image when we mix them. For instance, here we can enumerate them, say 1, 2, 3. And they will appear in the image as 3 to 1, right? So we need to code somehow this order, how do they appear. If we know the length and we know the combinatorial part responsible for our mixing, we know the whole map. Do you agree? So we will code this mixing by permutation, because it's rather convenient for us. But permutation we will interpret in a very naive sense. We will not think that 1 goes to the place 2. We will just write it as 2 lines, and on the upper line there will be an order of the intervals on the top level, and in the bottom line there will be an order of the intervals in the bottom level. So when we are talking about minimality and other properties, there is one very natural obstacle that may happen that kills all our dreams about minimality. Namely, it may happen that our permutation splits into 2 independent parts. What do I mean? For instance, it's the situation when you have 4 intervals and you have some business between 1 and 2, they flip, and 3 and 4, they flip. But they never go to this part occupied by these guys, and those who were on 3 and 4 have no chance to visit the country where 1 and 2 live. So they have a kind of an iron curtain between these 2 parts. And if you have such a property, of course you cannot hope for any minimality, because if you were born on one half, you will never go to the second half, and no matter what, right? So you cannot believe that there will be some orbits that are everywhere dense. So we would like to forbid such a situation, and we will use the word reducibility for it. So we will say that this permutation is reducible, and the one that doesn't have such a bad property is irreducible. Be aware, because the people at the first year at the university usually study in algebra more sophisticated notion of reducibility of permutations. But we are very naive people, we don't do such a serious effort. So I will assume that all my permutations are irreducible then. So they do not split into 2 independent parts. And if this is true, then I claim that typical interval exchange transformation is indeed minimal. And this result is due to Michael Keane. I think it's 1975. So he proved the following thing, that almost all interval exchange transformations with irreducible permutations are minimal. In reality, he did more than that. Namely, he provided quite a cool-looking sufficient condition for this minimality. What do I mean is that he said that the following thing, that the sufficient condition is that the singular orbits, by singular I mean those who are the ends of the intervals or their images. They, unless they are ends of the whole support interval, they do not meet at the same orbit. In particular, if our interval exchange transformation had rationally incommensurable lengths, он доказал, что почти все минимальны, но при условии, что перестановка неприводима. Значит, почти все в следующем смысле. Смотрите, для того, чтобы задать перекладывание, если перестановка задана, нужно задать вектор длин. Давайте мы договоримся, что мы живем в условиях, когда сумма длин равна вашему любимому числу, ну, от нормируемых. Тогда у нас будет симплекс в Rn, ну, там Rn-1, смотрите, сколько у вас отрезков. И, соответственно, в этом симплексе будет жить мера Лебега от природы. И почти все по отношению к этой мере Лебега.
Ну, у нас же есть еще перестановка, которая кодирует.
Ну, вот мы зафиксировали перестановку. И для фиксированной перестановки, если она не приводима, но если перестановка приводима, то понятно, что у вас не будет минимальности никогда. Если перестановка не приводима, то почти все дают нам минимальное перекладывание. Значит, это не вторая часть, это скорее следствие. Если наши длины рационально независимы, то те условия Кина гарантируют нам, что перекладывание будут, соответствующее перекладывание будет минимально. Ну, почему? Потому что Кин доказывал не совсем это утверждение, а то, что вот если точки не встречаются в одной орбите, Но как у них устроена орбита у этих точек? Смотрите, каждое отображение выглядит так, что мы вычитаем и прибавляем длины соответствующих отрезков. Поэтому получается, что если они встретились в одной орбите, это значит, что вы к каким-то длинам прибавили какую-то линейную комбинацию с целыми коэффициентами и получили еще одну длину. Ну, значит, они, получается, не будут уже у вас рационально независимы. Поэтому, если они рационально независимы, то никак вы не поразите с целыми коэффициентами для них линейную комбинацию, значит, они в одну орбиту не попадут. So, in this sense, this Kin's statement is very similar to what we had for the rotation of the circle, because exactly the rational or irrational angle corresponds to the existence or non-existence of the rational relationships between the length of the corresponding interval. And so this is already the moment to present you the first open problem in this context. Namely, as I told you, it's a sufficient condition, but it's not a necessary condition. So if I give you some family with some rational relations among the lengths, it doesn't mean that you cannot find the minimal representative in this family. Moreover, there are many families where you can find some sufficient number of minimal members despite of the existence of rational relations among the lengths. So the open question is the following. For an abstractly given family, if there is a smart algorithm how to decide either the majority of members of this family are minimal or non-minimal, if the family is described by the rational relationships among the lengths. And this problem remains still open. It's a plot of active work. And the very last thing, for instance, this morning I talked to my PhD student with whom we are studying some very new preprint by Vincent Delacroix, who announces that he has an algorithm that could provide the solution for this question, but for some certain families of the restrictions, not for a general statement. So it's still an open problem.
For some permutations.
Yeah, okay, you assume that permutations are irreducible, yes. So it's an interesting question, but of course, if you look on the question from the point of view of, say, physicists, you don't care about this measure zero situation when you have rational relations among the lengths, and you can concentrate just on the Kin's interval exchange transformations, on the generic ones, because absolute majority of them are like that. Ну, то есть вы попадаете на какое-то подпространство коразмерности 1, 2 и так далее, если вы вводите эти рациональные соотношения. Поэтому с точки зрения общей картины они ни на что не влияют. Okay, then once Kin wrote his paper.
Can we somehow formalize the notion that the number is very close to rational number, and so we should wait a long time when the orbit becomes dense, and to see something.
It's an interesting question how to attract this problem. People who are familiar with number theory, what they did, for instance, they considered special subfamilies. Bashar-Nitzan worked with interval exchange transformations of rank 2. So you have just two rationally independent lengths, and all others are given by their linear combination with integer coefficients. And so you live in the world of algebraic numbers or something like that, and you try to treat it, and he has some partial answers in this case. То, что это близко к рациональному, это разумная постановка вопроса, но как бы нам это не принципиально. То есть для того, чтобы такого типа наблюдения сделать, которое не qualitative, а просто будет она всюду плотна или нет, нам важно только, как в случае с поворотом, отличать, есть рациональное соотношение или нет.
Ну да, общее тоже смотрим.
Вот, so once Kin published this paper, already in this paper, he started to suspect that if typically they are minimal, maybe they are also typically uniquely ergodic. The question of the invariant measure looks very silly because, of course, there is a natural candidate to have an invariant measure, and this is a Lebesgue measure because all your transformations are just some combinations of shifts. They preserve Lebesgue measures, so you expect that you should have an invariant measure, and the question is how many you may have. And the answer was, he made it as a conjecture that almost all interval exchange transformations are uniquely ergodic. And it became a theorem. The theorem proved by Hovey Mazur and Bill Veach independently. In 1982, two papers in the same issue of Annals of Mathematics, where these guys prove that almost all interval exchange transformations are uniquely ergodic. So probably I have to comment on this fact that once again, by almost all, I mean in particular that they always lived inside of Kin's set. So whatever will happen after what I tell you now, people always assume that Kin's condition is satisfied. So the families where Kin's condition is not satisfied, it's a subject of independent research. And it's very non-generic, and we cannot use all the standard algorithms we know. So Mazur and Veach proved that they are almost all uniquely ergodic. They have two different proofs. One proof is much more geometric. So Mazur was thinking about Riemann surfaces, one forms on these Riemannian surfaces, modular spaces, and these kind of things, while Veach preferred more kind of dynamical point of view on it, and did not want to think about the geometric interpretation so much. So they provided the proof. Maybe at some point I comment more how it works, but not today probably. And then there was immediately a question: can we construct an example with some exception to this statement? Because what these guys did, it was not as nice and easy as Kin's observation, in a sense that they did not provide any description of this exceptional set or of the good set. They just made the statement about its measure, but we could not describe it so explicitly as we did in the case of minimality. So there are examples that are non-uniquely ergodic, so interval exchange transformations that admit more than one that admit more than one invariant ergodic measures. Of course, these measures are singular with respect to each other. So the first example is due to Kin himself. Then there were famous work by Keynes Newton and some other people. They were numerous. And now we can even estimate the possible number of the invariant measures that interval exchange transformation may have. So it's a theorem by Anatoly Katok that the number of measures cannot exceed the integer part of n over 2. So you cannot construct rotation on the circle with two invariant measures. It's forbidden. And even 3 intervals is not enough. Arnold in reality worked with the same thing as rotations. But starting from 4 intervals, you may think about it. It's a little bit rough formulation, because in order to make a precise statement, we need to think more about its connection with geometry. But today I don't want to do that. I want to give a very elementary exposition of what happens. And in reality, you can this estimation is rather sharp, so you can find examples with any number of measures between 1 and half of n. And it was proved later by different people, and we should mention Satayev, but he used the language which was very far from the one that we discuss now, and so the presentation, which is open for those who don't know geometry and topology, is due to John Fickenshire. So you can, now there are even proofs that of this statement that use a purely symbolic presentation, so you don't need to know any geometry at all. In any case, this is about the number of measures. And so I told you that I will tell you why people got their Fields medals recently. And I will mention a few results just to make it make you a bit familiar with these things. Then if one of you will be interested, we can give more talks about it, or I can give a more specific lecture.
There are less when ergodic
Yes,
measures.
yes, yes. So it's the following thing that now when we know that they cannot be, we know about their unique ergodicity, after ergodicity we can increase the level of requirements. We can ask about strong and weak mixing properties.
Sorry, and these are also delta measures for orbits. Yes.
No, because we assume that we deal with minimal interval exchange transformations. So if you take non-minimal one, indeed the invariant measure can be one that lives on one of your closed orbit, and that's it. But if you take a minimal one, you need to construct something more sophisticated as a measure. Правильно? Но у вас, если есть замкнутая орбита, то понятно, что у вас никакой строгой эргодичности не будет. Вы посадите туда меру, которая сидит на этой замкнутой орбите, а все остальное игнорирует. И будет она вам вполне эргодична. Все, что на этой орбите у нее будет иметь полную меру, все, что мимо нее будет иметь меру 0, и все. Но если вы рассматриваете минимальную, а мы интересуемся, конечно, больше минимальными именно по этой причине, то там, значит, мера должна выглядеть как-то нетривиально. И она не может так вот сидеть на какой-то орбите просто. И, соответственно, вот утверждение коллег, там, Катка и потом тех, кто пришел после него, в том, что мы можем померить, сколько таких мер допускается, но их может быть на самом деле достаточно много. И не так сложно объяснить, как устроены соответствующие примеры. So, as I told you, once we have ergodicity, we can ask ourselves about the mixing properties. So what does it mean to have mixing properties? You take...
Количество мер это какие?
Ну, это инвариантные эргодические меры.
Сейчас, а разве не комбинации будет?
Будет, но это имеется в виду, что это размерность соответствующего пространства мер не будет превышать вот этого числа. Вы правы, что... Более того, мера Лебега, она может быть не одной из тех, на которые натягиваются, а, собственно, комбинацией этих мер. Вот. Но это именно как размерность пространства соответствующих мер. Значит, so once we have... just a second. Just a second, sorry. So once we have this ergodicity, we can ask what about mixing properties. And mixing in mathematics we already discussed, I think, on your talk, right, Slava? We discussed what is weakly mixing and what is strongly mixing. So I assume that you know more or less what does it mean. Let me just recall you very briefly that if we have a space, it's measure preserving dynamical system, we say that we deal with a strongly mixing map if for any two measured sets this limit is a product of two maps, and we deal with a weak mixing in Cesare sense if we can say that these things so this limit is 0. So this is a strong mixing and this is a weak mixing. We discussed it when we were talking about geodesic flow and or cycle flow, and we tried to figure out what are their dynamical properties. So once you have something ergodic, you can naturally ask the question, what about interval exchange transformations when they are weakly mixing, when they are strongly mixing? And the first question about strong mixing was solved very fast, because Katok proved that they are never strongly mixing. And the second question about the weak mixing stayed much longer. Katok and Stepin observed that interval exchange transformations on 3 intervals that are not reduced to the rotation, they are weakly mixing almost always. But then many years passed. They did it at the early 70s, and it required like 30-something years to make the next step. And so there is a theorem by Arthur Avila and Giovanni Forni, who proved that almost all EETs that are not rotations are weakly mixing. And it was one of the results for which Arthur was awarded his Fields Medal in 2014. He had, I think, 3 main results. One was this one. Another one, I will comment on it next week when you present multiplicative ergodic theorem, because in we will apply this theorem in this context, and I will tell you what was the result that impressed so much the community. And the third result is not related at all to this business. It's a Ten-Martini problem and some properties of Schrödinger operators. So it's very different. In any case, one of the key results that he got, you can already understand. Not the proof, of course, but the idea what was done. It's the statement of weak mixing for interval exchange transformations.
Sorry, the second result follows from first.
No. The point is that it works like that. Maps that are ergodic, they are not necessarily weakly mixing, but if they're weakly mixing, they are ergodic. If they're weakly mixing, we proved here positive result, affirmative one, that they are weakly mixing. So if they are weakly mixing, they may not be strongly mixing, or they could be strongly mixing, just we are not able to prove it yet. Ну, смотрите, у нас, значит, есть 3 свойства. Есть эргодичность, есть слабое перемешивание и сильное перемешивание. Из сильного следует слабое, из слабого следует эргодичность. Обратные импликации не верны. Да, значит, Каток доказал, что они не сильно перемешивающие. При этом мы знаем, что они эргодичные. Соответственно, был вопрос, а слабо перемешивать они будут или нет? Потому что из сильного следует слабое, но сильного у нас нет. Из эргодичности не следует слабое, эргодичность у нас была. Слабое получается между ними, было непонятно, куда его. И вот Авила и Форни доказали, что типичное перекладывание, если это не поворот, оно слабо перемешивает, а сильного перемешивания нет.
Сейчас, а сильное это как раз...
Сильное это вот это? Вот.
А это слабое.
А когда вы к пределу Пачезера переходите, тогда слабое будет. Вот. Ну, просто для того, чтобы вы понимали, в принципе, какого типа результаты люди доказывают. Значит, мы поговорили про это.
Сейчас, а тут почему Чезаро? Это, ну, можно же другие пределы смотреть, или это просто так получается?
Не, ну этого есть физический смысл, так как эта вся наука вышла из статистической механики и термодинамики, то у такого есть понятный физический смысл.
Можно сказать функционально-аналитический. Вот говорил функционально-аналитический смысл строгого перемешивания. А слабое перемешивание, значит, что все собственные функции — это константы.
Угу. Можно, да, это то, что, ну, спектр дискретный там, если угодно, да. Это, когда доказывают, то часто оказывается даже более удобным утверждением. Ну, хорошо, наверное, мы на этом сегодня закончим, потому что я не хочу ничего доказывать, так как в следующий раз нам придется прерываться на другие темы. Но мы вернемся к этому, так как Маша собирается делать доклад, и если у вас будет интерес, то я, соответственно, какие-то из этих утверждений докажу и расскажу, что еще люди делают в этой связи. Но мне кажется, это будет интереснее после того, как станет понятно, как это связано с другими более наглядными динамическими системами. Эти утверждения можно сформулировать, используя одно определение. А чтобы стало понятно, почему люди так бились за это, лучше рассказать, но я не хочу спойлерить потенциальный доклад. Okay, so thank you for your attention today, and see you next time. We will listen to the proof of multiplicative ergodic theorem, and then you start with Oppenheim conjecture.